We've seen that calculations involving addition and multiplication mod n are relatively straightforward. In particular, we can replace any integer by the integer between 0 inclusive up to n minus 1 inclusive, to which it is congruent. However, when we come to exponentiation, the situation is not quite so straightforward. If we take two integers a and b, which are congruent mod n, then it will also be true that a to the k will be congruent to b to the k mod n. And that follows simply from the fact that a to the k is just a multiplied by itself k times. So really this is just an example of what happens with multiplication. But on the other hand, if we take a number k and raise it to two powers, a and b, then it's not the case that a is congruent to b mod n implies that k to the a is congruent to k to the b mod n. So in other words, if the bases are congruent and we're looking at a fixed power, then we do have that a to the k is congruent to b to the k. On the other hand, if the bases are the same and the powers are congruent, then as happens in this situation here, then it does not follow that k to the a is congruent to k to the b mod n. And the counterexamples are rather simple. 1 is congruent to 4 mod 3. But on the other hand, if I take 2 to the 1 and 2 to the 4, then 2 to the 1, of course, that's just 2 and congruent to itself mod 3, whereas 2 to the 4 is 16. 16 is 15, which is a multiple of 3, plus 1. So 2 to the 4 is congruent to 1 mod 3. So it's not the case that because 1 is congruent to 4, that 2 to the 1 is congruent to 2 to the 4. That's not correct. So that's the first thing of which we need to be aware. The second matter is that we're going to need to calculate a w to the d mod m for extremely large integers. So typically, w, d and m may each have 300 digits. The naive method to do this would be to continually multiply w by itself, d times, and simplify the result to give something less than 300 digits. But the number of multiplications we have to do is far greater than the number of atoms in the universe. So we're going to find there is indeed a much better method of doing exponentiation. So let's just take a toy example, which we'll calculate in the next slide. Take 19417 to the power 1431 and take it modulo 7218. Even that would involve, if we were going to be naive about it, 1,431 multiplications. However, what we'll find is that you can do this calculation with just no more than 10 squarings, multiplying the same number by itself, about 20 long divisions and 10 multiplications. And we're going to, in fact, do this by hand in the next slide. In the case of RSA, as I said, where we have 300 digits for each, possibly for each of W, D, and M, then we can also do it, or at least the computer can do it, with less than 900 squarings, multiplying an integer by itself, 1800 long divisions, and 900 multiplications. And that, even when you're dealing with 300-digit numbers, is rather trivial for a computer.